All right, hello and welcome to our predictive analytics investigation titled Predicting Injury Severity with Crash Data. We are Team 10, and on the next slide, we'll be introducing ourselves and just talking a little bit about ourselves. After that, we will kick it off and go into the details of our investigation.
My name's Riley, and I'm an MIS 4+1 student here with the concentration on data science, and I will be graduating in May of 2026.
My name is Ethan. I am also an MIS 4+1 student, and I'll be graduating fall 2025. And my concentration is information assurance.
My name is Rena Han, and I'm a master's student in Business Analytics and Data Science program, and I'm graduating this spring.
My name is Rohit Sadesh Nair. I'm also a master's student in Business Analytics and Data Science program, and I'll be graduating in the spring of 2026.
So just kind of a really high-level overview of our investigation. Our data was collected by the National Highway Traffic Administration, and it is a collection of data relating to highway traffic accidents. And our primary objective is to look at all of the variables collected by the National Highway Traffic Administration and try to see if there is a link to injury severity with the drivers that are involved in the accident. The dataset consists of 28 total variable files, but we're only focusing on 4 of them, both for the sake of simplicity and also because the other variable files weren't as related to the crash as we would have liked them to be, so we focused on those 4. We ended up creating 4 different predictive models to determine injury severity that we'll go into more detail about later in the presentation.
Our goal in this project was to create predictive models that can show which factors are most influential to determine the injury severity in car accidents. And we analyzed various factors, including driving patterns, driver demographics, road and vehicle conditions, potential distractions, and environmental influences. And the insights we gained can help improve highway safety by pointing out where actions are needed most based on the data we have. And ultimately, our research can give organizations some insights to help reducing risks and making roads safer for everyone. For our data mining goals, we applied 4 different machine learning models, including decision tree, random forest, naive Bayes, and logistic regression, to see how well they could predict injury severity. The key was to find patterns between our input variables and the likelihood of a major or minor injury. Once we built our models, we focused on choosing the ones that can offer best balance between accuracy and interpretability. So the results are not just correct, but also easy to understand for our end users. In the end, we were trying to turn complex data into insights that can actually make sense and can drive better decisions. For our project structure, we followed the CRISP-DM framework, which is a standard approach in data science for guiding predictive analytics projects. And it gave us a clear process from understanding the business problem, preparing and modeling the data, all the way through evaluation and potential deployment. For the analytics part, we worked entirely in KNIME, which allow us to manage data preparation, build models, and evaluate results effectively and efficiently. Besides that, we used different tools to keep track of progress and Teams communication, including Word document, Excel, and Teams chat throughout the project.
Data understanding is a crucial part because you have to know what you're working with. And as Ethan mentioned earlier, we were provided with about 28 different files, all with different factors that go into crashes, but we keyed in on these 4 different tables: vehicle, distraction, person, and accident, because we felt that these contain the most relevant features, or I guess information about the circumstances that went into each automobile accident around the United States in the year of 2021. Data quality is crucial because you have to be working with valid data so that your models can make accurate predictions. And so to do so, we utilized a lot of rule engines and missing value nodes, and then numerical binders that I'll talk a little bit more about in the next slide. But before we even started data preparation, we had to make sure that we were keying on in records that were, I guess, relevant to our study. And so, for example, we only wanted to study people that were sitting in the driver's seat. So we filtered out all the rows that had seat positions that were not equal to 11, which was that of the driver. The other one we did was body type. We wanted to focus in on non-commercial trucks. So we wouldn't have 18-wheelers because, as you can imagine, those results would be far different than a small little sedan. So data preparation took up about 80% of this entire process. It's crucial to have clean, good, valid data to feed into your predictive models so that you can have the best possible outcomes. And as you can see, we used a rule engine and missing value node and numerical binders for almost every single variable that we used in our predictive model. And the rule engine pretty much filtered out all values that were above a certain number. So for example, a lot of these variables would have a value of 99 or 999 if it was missing, unknown, reported, whatever it might be. And so we wanted to filter these out to make sure that they weren't influencing our predictive models in a way that we did not want it to. And then we used the missing variable or the missing node to impute values that were either the most common values or the mode, median, mean, whatever central tendency measure made the most sense for that specific variable. And then numeric binner transitioned or transformed our variables from numeric into nominal because that helped our predictive models and were easier for them to understand. Again, as Ethan mentioned earlier, we ran 4 different types of predictive models. One was our decision tree, which is one of the most simple types of models that there is. It basically just branches out into a bunch of yes and no questions. And if you answer yes, then you start down one route. And if it's no, it's the other route. And it goes all the way down until an answer is reached. A random forest is a bunch of very small decision trees. And each decision tree within the random forest gets a vote towards the overall prediction. And whichever classification has more votes in the end gets the prediction. The naive Bayes model is more probabilistic, and so it basically calculates the probability of a specific instance being in one classification versus the other, and it predicts whichever classification has the higher probability. Logistic regression is more statistical based and is very good at predicting binary targets, which was good since we split our target variable of injury severity into major and minor.
Okay, so once we selected our modeling techniques, we moved on to building the models. So we started by using the color manager to easily distinguish injury severity outcomes. And the irrelevant columns like the unique identifiers were removed to prevent noise in the models. Also, the nominal variables were converted using one-to-many encoding to make them machine readable format. We also normalized the vehicle age to ensure consistent scaling across inputs. And one of the important factors is like to prevent overfitting, we partition the data into training and testing sets. Also, since the classes are imbalanced, we applied equal size sampling to balance the major and minor injury categories. And finally, we connected the process data to each of our 4 learner nodes to build the predictive models. After building the models, we evaluated them based on 4 criteria, which is accuracy, sensitivity, specificity, and their ROC value. So naive Bayes had the highest accuracy at 82.55%, but its ROC score was lower compared to logistic regression. The logistic regression offered the best balance overload with the highest ROC value at 0.862 and strong specificity. But the random forest also performed very well across all metrics, providing a robust middle ground option. And while the decision tree was the easiest model to interpret, it shows the weakest performance in terms of overall metrics as shown from the ROC color on the screen. And moving forward towards our observations and recommendations. So based on the key variables influencing injury severity, we have several targeted recommendations. First of all, stricter seatbelt enforcement and public awareness campaigns are crucial since whether the restraint system was used or not including the seatbelt matters a lot towards the intensity of the injury. Second, improving post-crash medical response can significantly reduce injury outcomes. We also suggest deploying better crash prevention technologies and encouraging regular airbag system checks. Also, addressing drug-impaired driving through stronger laws and roadside testing is another important step. And lastly, investments in better road maintenance, signage, and tailoring interventions to urban and rural crash patterns are very necessary. To summarize, we built and evaluated 4 models to predict injury severity using crash data. Logistic regression emerged as the most balanced and effective model. Random forest and naive bias also provide valuable insights into injury patterns. Overall, our findings can inform targeted strategies to enhance highway safety based on predictive analytics. And hence, we have met the objective of this particular investigation as mentioned in the business understanding. So, thank you. And we are happy to answer any questions on the discussion.